right, thank you for joining me today. My name is Thomas Kenny. This is the final presentation on my topic, predicting heart attacks, the impact different health statistics have in causing a heart attack. This is from my Data 690 capstone, and we'll continue forward. Let's go. Today we'll just briefly go over the scope, the problem definition, and reviewing the data set. Briefly, because we've already went over this in the previous presentation. The remaining portion of the presentation will be discussing the visualizations and predictive models that were created, the findings from these predictive models, and then the key performance indicators we mentioned in the last presentation will be discussed briefly, as well as the lesson learned today. Okay, as mentioned in the first presentation, the scope, heart attacks and cardiovascular diseases have plagued humanity but we're focusing today on the United States. Since at least 2000, every 40 seconds, again, someone dies of a heart attack, and heart attacks have become a massive issue that plagues the United States yearly, causing a lot of death, a lot of anguish, anger, sad, everything, along with a lot of economic loss. The main cause to be for a heart attack is when the blood supply to the heart becomes narrowed or blocked completely, which would trigger the heart attack. Again, back to the economic cost. Again, in 2010, a study was conducted determining that about 177.5 billion US dollars was the cost of a heart attack, and in another study conducted in 2019 and 2020, 422 billion dollars went towards heart attacks, either that being to pay for medicine or hospital stays, to also loss of productivity due to people dying. The data set chosen today was created by Ankush Pandey, and I got it from Kaggle. It has 32 different variables with 372,000 rows of data. It is a very large data set. I'm not sure how Mr. Pandey got the data. It does indicate that he got it from 3 different web sources. The data was collected again from November 17, 2019 to July 11, 2024, and it indicates it should be updated annually. Okay, the first visualization we have here is a 3D scatter plot. Here we have on the x-axis we have education level. On the y-axis we have employment status. The stress level variable is on the z-axis, and then the color of the different points in the graph is based on the outcome variable. Okay, as we can see, just by looking at it briefly, somebody has more of a chance of having a heart attack if they're employed versus being retired or unemployed. We can tell this because if the little square cube is purple, that indicates a heart attack, and the teal color indicates no heart attack. A patient is least likely to have a heart attack if their stress level is 1, 4, or 8, regardless of any other variables. Somebody is more likely to have a heart attack if their stress is a 6 or a 7. And the education variable alone was not a good indicator to determine who would have a heart attack or not. Most of the most influential variables in this graph were employment status and stress level. Moving on, we have a 3D bar graph that shows the physical activity on the x-axis, the diet variable on the y-axis, and the outcome variable on the z-axis, with the physical activity also being the color, just so we can better depict each different area. A person is least likely to have a heart attack if they have a healthy diet in a physical activity level of 3. So if you eat a healthy diet and you kind of have like a middle of the pack workout plan or situation, you would be least likely to have a heart attack. The next set of statistics will be people who are most likely to have a heart attack. Starting off, we have an unhealthy diet and a physical activity level of 0 and 3. Then you are more likely to have a heart attack. A moderate diet with physical activity 0, 3, and 6. Again, that would be more likely to have a heart attack. Surprisingly, a patient who has a healthy diet but a physical activity level of 1 or 2, which is low but you're still active, you would have an increased chance to have a heart attack, which, again, that's surprising because if you ask most people, if you work out a little bit and have a healthy diet, people would think you're better off not having a heart attack. But according to this data, that's not necessarily the case. You have an unhealthy diet, but your physical activity is between levels 3 to 6, and you're still more likely to have a heart attack compared to someone with a physical activity level 2. So if you're unhealthy diet and you have a physical activity level of 2, you are less likely to have a heart attack versus levels 3 to 6, which is, again, that's kind of hard to understand because you're more active, so you would think being more active would decrease the chance, but I'm guessing not. It's looking like maybe depending on the diet might be the bigger factor in all this. With a healthy diet and a physical activity of 1, 2, or 4, you'll be more likely to have a heart attack. Lastly, with a moderate diet and a physical activity of 0, 3, and 6, you will be more likely to have a heart attack. So again, this this grouping, this graph is kind of going against the norm, and I'm not really sure why. I mean, that's just the data that's been collected. So maybe with this sample size, the data is depicting something different. Obviously than what people might think, that if you have a healthy diet and you work out even just a little bit, you should be good to go. But again, this visual is going against the norm. Let's move on. The last visual is a 3D surface plot showing the relationship between the variable smoker, which is the z-axis, heart rate, which is the x-axis, and cholesterol, which is the y-axis. Outcome, again, is going to be used as the color. Right off the bat, purple indicates there was a heart attack, yellow indicates there's not. There is more purple than yellow. Even when you move the graph around, it does seem to depict more purple than yellow. If a patient has a cholesterol of 300, a heart rate around 120, and smokes, they're more likely to have a heart attack based on this graph. If someone smokes, and has a cholesterol of below 250 and a heart rate in the lower 60s, you are less likely to have a heart attack. So it seems that the heart rate and the cholesterol factor into more to protecting you from a heart attack than smoking does in that instance. And then overall, though, smoking seems to be the stronger or more influential variable, because at various different levels of cholesterol and heart rate, you're still more likely to have a heart attack compared if you don't smoke. Okay, moving on. This is just a sample size of 10 of the predictive models that were created and some of the metrics for them. Overall, there was about 75 models created between SAS Enterprise Miner and DataRobot. Enterprise Miner is a software you can download to generate models and different and visualizations, which the visuals that we looked at previously were created via Enterprise Miner. DataRobot is an online website that you can go to, and it'll auto-generate. You can manually put them in, but it'll auto-generate numerous amount of models. Very useful tool. And then, so the first model, which would be from DataRobot, was Carboxylin Neural Network. It is number 8 in the purple square. This is a deep learning model. It utilizes skip connections to connect different layers of the neural networks. The neural network which helps mitigate the vanishing gradient issue in deep learning. The vanishing gradient issue is when the gradient is used to model is going to be a neural network as well. It is labeled in the red box number 3, but this model was created in SAS Enterprise Runner. Again, everything is, for the most part, similar to the data robot model. And then the third model that was created was a SVM, or support vector machine linear model, created against Enterprise Runner. Support vector machine model is a model for classification issues, which is the one we're dealing with today. They require classifying the element, or they classify the elements of a data set into 2 groups, like yes or no, or cat or dog, things like that. So moving on, we will focus on the findings, or how the models perform. Overall, we will break down the different metrics with confusion matrix. Confusion matrix is the main way to help determine if certain models like this one like these, to see how well they perform. We have 4 different metrics we like to look at: accuracy, precision, recall, and F1 score. Accuracy is how often the model is overall correct. Precision is measures how often the model is correct measures how often the model is correct at predicting the target class. Recall measures how many times the model can find the target class. And F1 score measures the harmonic mean of recall and precision, which is the average rate of change. We can see an example of what confusion matrix is. We can see the top left section is saying that the model predicted to be true, or predicted the end outcome to be true, and it was correct. And then below that is predicted to be true, but it was false. And then on the right side, we have the model predicted to be false, but it was positive, so it was incorrect. And the model again below that predicted to be false, but it was false, so it was correct. All right, on to the findings. None of the models created performed well. If we look back at the different accuracies, the best model based on just, accuracy alone is not a good measurement to determine how well a model performs, but the SVM linear model performed the best in that regard. And but everything else, across the board, is 0.64 accuracy, 0.51 precision, 0.53 recall, with 0.52 F1 score. These are the top 10 models that were created. So overall, the models did not perform well. There's a few reasons that this could have been the case. First one could have been overfitting. That's when models learn to train data too well, and this can happen by the model capturing noise and then fluctuations rather than the underlying pattern. In order to try to fix this, you can use regularization techniques, like L1 or L2, and cross-validation to help prevent this. I will note that the data robot models do have a built-in cross-validation process that they run when they create the models, and again, those did not seem to increase the model's overall performance. The next issue that could have happened would have been insufficient data. This is when not enough data in the data set. This is when there's not enough data within the data set to create a reliable model. Collecting more appropriate data will help mitigate this issue. The quantity of this data set was over 370,000. So the quantity probably was not the issue. Maybe it could have been data quality, which is the next issue that we're going to talk about. The data quality is when the data set has a lot of missing values or it's biased. Making sure the data set is clean and processed correctly will help mitigate this issue. The target variable for this data set was split almost down the middle, so it was like 50x, 50